So let's talk a little bit about this exponential. Y equals negative 2 to the x. I'm in my notes. I'm on the back of page 1 of the chapter 3 notes. So y equals negative 2 to the x. Now, our baseline exponential that we've been using in the last couple that we did is y equals 2 to the x. This is the 0.01. That is what an exponential looks like. Okay? Now, yesterday we talked about what happens when we put a negative on the x. What happens when we put a negative out in front of the problem?
Flips upside down.
Exactly. So you're going to take that picture right there and you're going to turn it, we call it a reflection across the x-axis, but you're basically going to turn it over. So instead of containing the 0.01, it's now going to contain the 0.0-1. Its asymptote's going to stay the same because we haven't lifted it up or down. We simply reflected it across the x-axis. Good job. Now, this next one, a little bit tricky. And it's tricky because the classic exponential curve, this curve, which probably should be your starting point when you graph exponentials, counts on the base being bigger than 1. So what I need for you to think about is that 0.5 is 1/2. I mean, you don't really need to think about that, you know that. 1/2 is 2 to the negative first. Now, does that make sense to everybody? 1/2 is 2 to the negative first. When I deal with exponentials, I want to have my base greater than 0. Or greater than 1, I mean, it's always greater than 0. I want to have it greater than 1. Now, what does this look like? Remember, here is the basic exponential. What happens when we change the sign on x?
It flips across the y.
Exactly. I kind of missed there, but it flips across the y-axis. So this right here, that is the 0.01, and this is 2 to the negative x, which is the same as 1/2 to the xth power. Now, what does this do to it? This +1 stuck on the end.
Moves it up 1.
It does. Now, that's going to change a couple of things. First of all, its intercept is going to be at 0,2, right? And the asymptote that was the x-axis also gets moved up 1. So now we have an asymptote at 1, and our curve coming down like this. Okay? So the lesson maybe to come out of that problem is, don't get fooled. Don't try to graph your exponential until you have converted your base to a number bigger than 1. Because as soon as you have a base bigger than 1, then you know this is what it looks like, this dashed line. And then you can make whatever modifications are necessary. Continuing in that theme of growth versus decay, that is dashed black line versus solid black line, we are looking at this. We're going to determine whether it represents growth or decay, and then we're going to talk about its end behavior. Now remember, end behavior is the limit as x approaches infinity of the function, and the limit as x approaches negative infinity. of the function. That is end behavior. It's what happens at the ends of the picture as x goes all the way to the left and as x goes all the way to the right. All right. Take a look at this guy. What does this look like? Are you comfortable if I draw that in like that? Yep, Jesus is nodding his head. He's exactly right. This is what an exponential looks like when the base is bigger than 1 and the exponent is positive. Now, end behavior. What happens to my curve as I go to the right? What's the limit as x approaches positive infinity? What's happening to my curve?
It's going up.
It is, so positive infinity. Now, what happens as it's going to the left? Now, don't say it's going down. It is going down, but it isn't going down, 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 down. It's going down and is bounded by what?
Zero.
By 0, the asymptote, the 0, and it's from the top of the asymptote, right? The curve is coming down towards 0. Remember, for an exponential, your asymptote's at 0, unless you've moved it around. The asymptote's at 0, and this curve is coming down and approaching that asymptote from the top. So that is the end behavior for that one. Now, what about this one? Isn't that the same thing we just drew, except reflected across the y-axis? Yep, I see some more nods. That's awesome. So what is that end behavior? I'm going to save myself some writing and just erase these. What is that end behavior? Well, what's happening as we head out toward the right? What's happening as we go that way this time?
Getting closer to 0.
Yep. From the top again, so we'll put a little plus sign there. From the top. And what's happening as we come to the left? Come this way. What's our curve doing?
Going to infinity.
It is. There you go. Beautiful, beautiful, beautiful. Now, be careful on the next one, you guys. You've got to be able to visualize it, and the shape of it's going to be either the one I just erased or that one right there. That's what exponentials look like. Be careful, because this time your base is less than 1, and that matters. Okay? So somehow, whether you recognize that when the base is less than 1, it's decay, and that's fine, or whether you recognize this is really this, either way, you've got to see that this equation graphs like that. You're not going to have a calculator for this, guys, so you've got to know what that looks like. Does that make sense to everybody? That that one's going to look like that? So I'm not even going to erase this end behavior, because isn't that the same end behavior as we just had for this problem? Yes. Yes. So again, it doesn't matter to me whether you think of this, see this 1/2 and say, oh, the base is less than 1. That means decay, going down. Or if you convert it, and notice you've got a reflection across the y-axis. However you think about it, it really isn't important. What's important is that you know that's what that picture looks like. Now the next one is the ultimate in trickiness. I'm going to think of 0.75 as 3/4. 3/4 to the negative x could be written how? Another way. Four-thirds to the positive x, because a negative turns you upside down. Now, this is a basic exponential. This one has a reflection, this one doesn't. This is a basic exponential. The base is bigger than 1, so this is actually a growth problem. Remember that if the base is less than 1, you're decay. But if you have a negative x, you've reflected. So when you reflect a decay, you get a growth. You've got like a double decay thing going on there. So they kind of cancel out and you end up with a growth function. So what's our end behavior? Well, as we go to the right, as we go toward positive infinity, as we go to the right, our curve is going up. And as we go to the left, it's coming down from the top. Anybody have a question about part 5? All right, now we're going to look at some logistic functions. We're going to do some work with logistic functions in this chapter too. Also, do you guys remember what the logistic function looks like? Think of your BFFs. Do you remember which one it is? I hope someone remembers and you're just being very quiet today. The logistic function is the one, the basic one, is this between, has two horizontal asymptotes kind of trapped in there between 0 and 1. That's what the logistic function looks like. So notice that it has a Y-intercept and it has two horizontal asymptotes. Every logistic function, now we're going to move it around or stretch it and stuff, but every logistic function is going to have two horizontal asymptotes and a Y-intercept, because somewhere in there that curve's going to cross the Y-intercept or cross the Y-axis. All right, so let's look at our first equation. Okay, now let's start with the Y-intercept, because that one should be the most obvious to you. What do we know? I'm going to erase these for the time being. What do I know about this point right here? I know one of these two numbers. What do I know about my Y-intercept?
It's 0.
X is 0, absolutely. If you are on the Y-axis, X is 0. So I'm going to come over to my equation, and I'm going to put in 0 for the X. And I'm not going to be frightened, and I'm not going to use a calculator. I can do this. You can do this. What's anything to the 0 power? 1. So I have 12 over 1 plus 2 times 1, right? What's 1 plus 2 times 1?
3. That should equal 4.
So my Y-intercept is at 4. It's that easy, people. Now, sometimes you're going to get a fraction. No big deal. That's your Y-intercept. Simple. Now your asymptotes are actually your in behavior. We're asking ourselves, what happens as I keep going right, what am I approaching? And as I go left, what am I approaching? So you're going to come over to your equation and you're going to ask yourself this question. Again, you're not putting this in on the calculator. You don't need to. You're going to say, okay, I want to know what happens as I come to the right. In other words, as x approaches infinity. So think about letting x be a big giant number like 1,000,000. Just think about it. I'm not going to calculate it. I'm just going to use my noggin. What happens when you take a number less than 1, 0.8 in this case, and you raise it to higher and higher powers? In other words, what happens as you keep multiplying 0.8 times itself? Is that getting bigger or smaller?
Smaller.
Very small. If you go far enough, this gets very, very, very small. That gets super tiny. 0.8 times 0.8 is 0.64. Times another 0.8 is, I don't know, point something. Smaller and smaller and smaller. Now, if this is getting very, very small, then it is getting closer to 0. 2 times 0 is still 0. 1 plus 0 is 1. So if x gets really, really big, this part goes away, and all I have is 12 over 1. So my top asymptote, which is often referred to as the limit to growth, when that number is 1, you got to be careful. If that number is not 1, your limit to growth would be whatever this over this is. But this is usually 1. Now, what happens the other way? So now think about making this not positive 1,000,000, but negative 1,000,000. Now think about it. Just think about it. You have 0.8, I'll say 8/10, raised to a negative 1,000,000th power. What does that negative do to this fraction? Turns it over. So now it's bigger than 1. The fraction is bigger than 1. And I'm raising it to 1,000,000th power. So what happens if you take 1.25 times 1.25 times 1.25 and you just keep doing that? Is your number getting bigger or smaller? Kids, what happens when you take 2 times 2 times 2 times 2 times 2? Gets bigger or smaller?
Bigger.
Yep. Anything bigger than 1, if you keep multiplying it times itself, it's going to grow. That's exponential growth. The base is bigger than 1. It's just going to keep getting bigger and bigger and bigger. So as this keeps getting bigger and bigger and bigger, isn't your denominator just getting huge? So you have 12 divided by some huge number. Tell me about 12 divided by a huge number. Big or little value?
Little.
Very little. And, excuse my language here, but the huger that gets, the littler this gets. So the farther I go that way, the smaller this gets, so the asymptote is at 0. It's going to stay positive, but it's going to keep getting smaller and smaller and smaller. So the key is to recognize that When you raise 0.8 to a positive power, it gets bigger. Smaller. 0.8 to a positive power, it gets smaller. So this basically disappears from the problem and you're left with 12 over 1. When you let this be negative, going that way, if you raise this to a negative power, this actually gets bigger. And the denominator gets so big that it makes the fraction get so small that it approaches 0. So the horizontal asymptotes for this problem are between y equals 0 and y equals 12. Now, before I erase all this, for those of you that don't understand any of the logic there because you're not really tuned into thinking today, what would happen if this were a 0.7? Would anything change in the conversation that we just had? No. Nope. Nope. Doesn't matter. Doesn't matter. That topic, this is going to go away and the asymptote's going to be at 12 over 1. If this were a 0.6, doesn't matter. That all the basics right there are going to stay exactly the same. All right, so let's look at the next one. Okay, and I need my intercept and I need my asymptotes. Okay? So here we go. How do we find our y-intercept again?
Plug 0 in for x.
Yep, and when I plug a 0 in there, this turns into 1. So this turns into 5. So the whole denominator turns into 6. 18 over 6. Would you say your intercept's at 3? Now, what about our asymptotes? Well, remember, that's less than 1. So as this gets really, really big, this gets really, really small. So where's that limit to growth? Where's that top asymptote? 18. Now, as x gets negative, it turns this into a 5. It turns 2/10 into 10 over 2. So that starts growing, 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 which means this gets huge, which means the fraction is approaching 0. When the denominator is outpacing the numerator, it's going to go to 0. Fractions that are bigger on the bottom are approaching 0. Now let's not freak out when we look at this. Can I rethink this? Like that? So that it kind of looks like all the other problems that I've done? So 1 over e, remember e is like 2.718. So this is like 1/3 basically. E is 2.7, so about 3, so that's like 1/3. So it's just like 0.2 or just like whatever the other decimal we had was.
So I have a question.
Uh-huh.
Would the x, if you were to format it that way, would the x not go on the bottom of the e?
Well, it doesn't make any difference because 1 over e to the x is the same as 1 over e to the x. Remember,
Okay.
1 to any power is 1. So it doesn't matter which way you write it, but it fits the pattern I've been using here if I put the whole thing to the x power. All right, so here we go. Put a 0 in. What do we get? What's that thing equal if we put in a 0?
1.
Well, this equals 1.
It'll equals 3.
So the whole thing will equal 3, yep, because this is 1 times 2 is 2, plus 1 is 3, and 9 over 3 is 3. Good job. What's my limit to growth? What's my top asymptote? This is going to 0, so it's at 9. That's exactly right. It's 9. And what's the floor of this? 0. The bottom asymptote's always going to be 0 unless you have done something like this to your equation. Because that, of course, will shift everything up. But remember, the whole idea here is, guys, and I can tell by the looks on your faces, you're resisting thinking about this. You've just got to. As x gets bigger negative, so technically smaller, but becoming a bigger negative number, this gets huge. And when this gets so huge, it completely dominates the fraction. You have 9 over 18 billion. That is just about 0. And that's what's always going to happen when you raise, when your base is a number less than 1 like that. Okay. Next, we have a few word problems to look at. So here we go. Got an equation that's been given to me. I'm on page 2 now, number 7. The number of bacteria is given by this equation. Boy, my old eyes can barely read that. All right, I think I got it right. What is the initial number of bacteria present? All right, pay attention to what this equation stands for. The number of bacteria after T hours. So how will we find the initial number of bacteria present?
Is it 100?
It is 100. Now, you might know that because you remember me telling you yesterday that this number right here in an exponential expression, like a times b to the x, which is what we've got right here, a is always the initial value. Or you may have reasoned it out, which is fine. That's always going to be the initial value. But if you reason it out, at the beginning, t is 0. No time has elapsed. Well, if you put a 0 in there, isn't your exponent 0? And e to the 0 would be 1. So you have 100 times 1. So even if you don't remember that that number is always the initial value, you can figure it out by letting t be 0. Don't forget to put a label on that. So it's 100 bacteria is what we're starting with. How many bacteria are present after 6 hours? How will I figure that out?
You plug 6 in.
It's exactly what I do. I'm going to plug 6 in for T. Now, you need a calculator for this, obviously. We're not doing this one without a calculator. Be really, really careful. 100. And then to get E, if you press second ln, it will pull up your E. And then just type 0.693 times 6. Now, if you didn't get 6,394 bacteria, I need you to say something to me because we need to figure out why you didn't. Did everybody get 6,394? Notice I rounded it off to the nearest whole number because I'm talking about organisms and I'm not interested in half organisms or 0.72 organisms. So we're going to round it off to the nearest one. now we've got some carbon dating here. So I've got an equation. Oh, you're going to have to help me out here. 0.000. How many zeros are there? 1, 2, 3. 1, 2, 1/16. Do I have 3 decimals after my decimal point. Is that what it says? Somebody with good eyes? Is that what it says? 3 zeros after the decimal?
Yeah.
Okay, good.
Yeah.
All right. What was the initial amount of carbon-14 present?
20.
Yep, 20 grams. And again, if you remember that in an exponential expression, this first number, not the one with the exponent, but the first one is always the initial value. If you can remember that, then you just look at your equation and say it's 20. If you can't remember that, then remember the initial value means t is 0. No time has passed. If you put a 0 in here, this whole shebang goes to 1 because this becomes e to the 0. So 20 is your answer. How much is left? Okay, B has 2 parts, so we'll do B1. How much is left over 10,400 or after 10,400 years? Well, won't we just put in 10,400 right here for this t? So 20e to the negative 0.001216 times 10,400. All right, let's see if we can all get the same
You
answer.
forgot a 0.
Oh, I did?
The point.
Oh, I did, yes, thank you.
It's like 0.00.
Yeah, thank you. That would matter to me, for sure. Remember, second ln is how you get your e. Also, remember that if you're putting in a negative sign, you got to use the negative sign, not the subtraction sign. I'll round it 1,000. Did you get 5.647 grams if you round off to the nearest thousandth?
Yes.
Good. That's wonderful. Now, there's a second part to letter B, and it says, when will the amount be 10 grams?
Do you replace C with 10 grams and then you go up through there?
Okay, now let's think about that for a minute. In the equation, in the formula they gave us, what does the C stand for?
That's for grams.
Yeah, that's the amount in grams. This is your gram amount here. What does the T stand for?
That's for years.
That's how many years. So when they're saying to me, when will the amount be 10 grams?
Can we just equal all that to 10?
Yeah, 10 equals 20 e to the negative 0.001216 t. Does that make sense to you? Now, that is a wild and wacky equation. But it is the reason that I have been looking so forward to this period all day. Because when your variable is an exponent, unless you can get a common base in your problem, which there is no way in heck we're getting a common base here, you need to use logarithms. When your variable is the exponent, when you have an equation and your variable is an exponent, we're going to use logarithms today. So We could. We absolutely could. Graph this side, find out where they intersect, and that would be our answer. You can do this without logarithms on your calculator, but by graphing. But we're going to do it using logarithms. So I want you to take a look at the equation, and I want somebody to tell me what very important step needs to happen before I do anything else. What do you think I might want to do before I do anything? Guys, we got to divide by 20. You got to get rid of that initial value. That's going to cause you all kinds of trouble if you don't get rid of it. So in this case, it's beautiful. I'll divide and I get 0.5 equals e to the negative 0.0001216t. Now, at this point, I'm going to take the logarithm of both sides. Now, you guys did this last year, so you already know there are two main kinds of logarithms. There are LOGs, which are base 10, and there are LNs, which are base E. Remember that LN is really just a base E logarithm. Whenever your problem involves an E, and many exponentials do, you are going to, it doesn't matter in the long run, but your life is going to be easier if you have an E in your problem if you use LN. So I am going to LN both sides of my equation. And we're going to spend more time on this, but since you have already done this last year, that really becomes this. The beauty of logarithms is that when you have LNE, they cancel out because this is the log base E of E, and that's just 1. So this part of the problem disappears, the LNE disappears, and all you are left with is the exponent. Now, solving for t is just a matter of dividing by that big decimal. So when I type that in, and by the way, be really careful, when you type it, when you hit ln, it puts a parentheses. Make sure you close that parentheses before you hit divided by. I got 5,700.224. Is it years? Yeah. Somebody's got a microphone on and you're listening to something that isn't logarithms. Oh, that was fun. That was fun. All right, we got one more. We'll do letter C and then we'll be done. Let's see if we can fight our way through this one. Did any of that look familiar to you? Do you remember doing that last year?
Yeah.
Good deal. That's wonderful. That's wonderful. All right, so here we go. Population. Now we've got a little logistic function. 19.875. Please tell me if I copy something wrong. I really am having a hard time reading this. negative point.
Would it help if I just read it out to you?
Is it negative 0.035005? Yeah, read me that exponent, Jacob.
Okay, so it's negative 0.0350005 t.
Perfect. Okay. All right, let's make sure we understand what we have going on. P is the population in millions. Okay, so in other words, if I get P as 2, that really represents 2 million. And T is the number of years since 1800. All right, we got to pay attention to what our variables stand for. All right, A. What was the population in 1850? All right, tell me what I'm going to do. How am I going to find my population in 1850?
Are you going to plug in 1850 to t?
I'm definitely,
Well, 50.
for 50, exactly. Did everybody catch that? That since T was defined as the number of years since 1800, we're going to plug in 50. Good grief, it takes longer to write it all out than it does to actually type it in. A little caution about this one. You're going to take 19.875 and you're going to divide it by this whole thing. So you're going to want to make sure that you have that whole denominator in parentheses. Whenever you divide by more than one thing, you gotta have it in parentheses. Let's see, 0.0350005. All right, I got 1.795. Did anybody get that, or did I make a mistake?
I got that too.
Awesome. Now be careful, don't just write that. It's 1.795 million people. That's your population. 1.795 million people. What will it be in 2010? Well, won't we do exactly the same thing? What will we plug in instead of 50 though? If we're going to do 2010, what would we plug in?
210.
210, right. So we're going to let T be 210. So I'm just going to put a 210 in there. Let's see what we get this time. I got 19.162 million people. Any confirmation with that? It's totally possible I typed it in wrong, so.
I think I got the same.
You got the same thing? Awesome. Good deal. Okay, our time is about up, and our next one, oh no, C, we got it, it wasn't what I thought. What is New York's maximum sustainable population That is its limit to growth. Now, think about those logistic functions we looked at before. Think about where the top asymptote's going to be. The top asymptote happens when all this disappears. So isn't your limit to growth going to be 19.875 million?
Yeah.
Yeah, it is. It is. So as long as this number is a 1, your limit to growth is always just going to be your numerator. Perfect timing. Good deal. Okay, let's put all of our math away.